name is Shakti Sharma, and today we are discussing one of the important topic of design and analysis of algorithm. I'm currently working as assistant professor in Bennett University. I have done my master's and PhD from IIT Bombay. I'm currently working on evolutionary algorithm, and my applications are on satellite image analysis, remote sensing. Now let's focus on the topic of today's discussion. So let me share uh, the OneNote file. So the amortized analysis. Now what is the amortized analysis? So if we consider algorithms in general, and we are much interested in the complexity of algorithms. So if we say that we have an algorithm, say named as algo1, which consumes, say, complexity of order of 1 in best case, and order of n in, say, worst case, and you have, say, 100 operations. Out of these 100 operations, 99 are best cases, and one operation is worst case. Okay, so I can directly write. Okay, best case is order of 1 and worst case is order of n. Okay, so this is, say, the complexity of this algorithm, and there we have, say, 100 operations. Now we want to calculate the average complexity of these 100 operations. Okay, so if we want to calculate the average of 100 operations, then we have to go with, say, the complexity total time consumption is 99 times order of 1, and one time it is order of 100, or order of n, basically what we have considered here. If we want to calculate the average, then we have to divide it by the 100 operations. So we get this equation, and we consider, say, 99 by 100 is equals to C1 and 1 by 100 is equals to C2. Then this operation is similar to saying C1 order of 1 plus C2 order of 100. Okay, so this is the way we can write it. So this is 1 by 100. This is another constant value, so I can replace it by C2 order of n. Okay, so if you have, say, gone through the complexity analysis, we can simply write it as order of n, because I mean, I'll not go much in depth for these asymptotic notation, but as order is determined by the highest growing function. Now here we have two functions, that is, one is of order of 1, another is order of n. The most growing function, we can say, is order of n. Okay, so this is how we can define these functions. So what we have just seen is that the average case complexity in these kind of algorithm is generally determined by the worst case complexity. Okay, now if we have, say, more operations and the worst case hit is too low. Now when I say too low, it is, say, of order 1 is to n. Then can we say determine the average case complexity not by the worst case but by the best case analysis? So that analysis is called as amortized analysis. We will just see. So it is the analysis of calculating the average case complexity of algorithms, especially done in the cases where worst case is hit very less number of times in general. So we will see this by two examples here. So the first example I am considering here is stack operations. Now, if I say the stack operation, I'm considering the following operation. First operation is a push operation on maybe stack S. So this operation is just pushing one more element in the stack. Okay, and then the second operation I'm considering is a pop operation. So pop operation is where you say pop one of the element from the stack. So deletion of one of the element from the stack. Okay, the third operation we are considering here is multi-pop. Now the multi-pop operation over stack S, and you want to say pop k number of elements from the stack. Now, if I say my stack is full with n number of elements and you want to delete, you can delete n number of elements by multi-pop if k is equals to n. So the worst case complexity of this multi-pop operation is order of n. Now, initially considering that you have say number of elements from these push pop and multi-pop operations, what will be the average case complexity? So if I say in general, the push operation complexity will be order of 1. Pop operation will be order of 1 because it's a simple insertion and simple deletion of elements. Now the complexity of multi-pop operation will vary. Okay, if there is say only 3 elements in the stack and you want to remove 10 number of elements, you can only remove 3 elements. So then the complexity will be 3. If you have say 10 elements and you want to remove 10 elements, then the complexity will be 10. So let's see how we can write this function, how we can say what we can say about the complexity of the multi-pop operation. Okay, so let's just see the algorithm of multi-pop operation. So multi-pop I want to do on operation S and K. So what I will do simply, I will check if S is not empty. Okay, so non is a function which will check if the stack S is empty or not empty. Okay, is not is it is if. Okay, and my K is not equal to 0. Okay, so suppose you are saying that you want to delete say 5 elements. Okay, so you have to see that stack has some element in it. Then what you will do is simply perform the pop operation on the stack. You will decrease the counter by 1. That means you have already deleted one of the element. Okay, and you will go unless either the stack is empty or you have deleted the k number of elements. So this is the generic say definition of multi-pop. Okay, so if I say that in your stack you have say L number of element at some point of time. Okay, so in your stack you have say L number of elements in. I want to say the complexity of this multi-pop function will be order of now minimum of say okay L comma K. Okay, suppose you said like you want to delete 100 element, but in a stack you have only 20 element, then you can delete only 20 element. If I say that you want to delete 100 element and your stack has say 1000 element, you can simply delete 100 elements. So the cost this loop okay, so we'll move on those many number of times. Okay, so instead of if, you can in say programming you can use while also. So while this condition is true, you will be moving on this and this and this and okay, so this is the thing. Now okay, I say the second example which we are considering is the binary counter. Okay, so the second example I'm considering here is a binary counter. A binary counter is a counter where we just increment the counter by 1 at every step. Okay, so there is a counter, we want to increase the counter by 1. Okay, so if I want to say the algorithm of binary counter, so binary say A is the name of the say array on which I want to use the binary counter, then I have to check condition that while A will go with some pointer I, okay, I can initialize I is equals to 1, okay, considering that my values are starting from 1, and then okay, so last say okay, I will just explain it in 1 minute. So I is less than a dot length, and I is equals to 1. Okay, so what we will do in this case, that we change AI into 0. Okay, and then in the end we will also check one condition. Okay, and we can say increment the I, check one more condition in the end. If my I is still less than a dot length, then make I is equals to 1. Okay, so let me explain what we just did in this algorithm. Okay, because some of you might directly understand, but I think I should explain it to rest of the batch. Okay, so okay, so this is say the array of binary counter. Okay, so I'm trying it here. Okay, and your number is say 1 0 1 0 1 1 1 1. Okay, and now if I want to say increase this counter by value 1, then what will I do? Okay, so the last index here, this particular index I'm considering as A1. Okay, this is A2, this is A3, and so on. Okay, and this is say the length of A. So I'm moving, if I say I'm moving in this particular direction. Okay, so this is how I'm moving in this table. So this is say counter. Now what we will do if we want to increase the value by 1, so we are simply increasing. We start from this end. If we encounter any number of 1, we will make them 0. Okay, and once we encounter a 0, we'll make it 1 and stop. Okay, so suppose first digit is 0, then you will make it 1 and stop. So what will be the updated counter if I say? So this will remain 1, this will be 0 1, and this 0 will become 1, and the rest of the values will be 0. Okay, so this is the increment the previous value by 1. Okay, if you wish, you can calculate the value in converting into normal decimal format also. Okay, so 1 plus 1 is 0, and there is a carry of 1, then 1 plus 1 is 0, carry of 1, and so on. And once you encounter a 0, the value will be 1. Okay, so this is how it is done. So now let's consider these two algorithms, and then we'll move on the amortized analysis part. Okay, so here also, if I say you have k number of bits, the maximum worst case possible is that all digits are 1, and then you convert all 1 into zeros. Okay, so the worst case complexity will be order of k if I consider it is a k digit binary counter. Okay, so if it is a binary counter of k digits, then the worst case complexity will be order of k. Now we want to calculate the average case complexity for both of these example. One is the stack operation and another is the binary counter of k digits. Okay, so let's see how we can do it. Okay, so there are say three kind of algorithms in our process and amortized analysis. Okay, the first one is the aggregate. Okay, first one is the aggregate method. The aggregate method is nothing but what we have just done. Okay, by say calculating the average case by adding the complexity of all the cases and then calculate the average case complexity. Okay, the another method is the accounting method, and in this particular method we account for the worst case in the beginning of the events. Okay, the third one is a potential method where we add a potential cost, okay, to subsidize the cost in the worst event. Okay, so these are the three cases. Okay, so what are these methods? So first method is the aggregate method. If I say want to write the aggregate method in a stack operation, so there are say n number of events happening in a stack. Okay, and you cannot remove an element unless it is not inserted in the stack. So if I say you have n number of events or operations from pop and multi-pop, and out of these say n number of operations, we have any number of push, any number of pop, any number of multi-pop operations. But what we know is that all the pop and multi-pop operation combinedly cannot provide a complexity of more than order of n, because you cannot push more than order of n elements if you are inserting say have push operation which is in the set of n number of operations. So you have at most n number of push operation. So your pop and multi-pop operation cannot remove more than n number of elements. Okay. So if I say the total complexity of this case will be of order of n, okay, of n operations, because you for push operation this is order of 1, for pop operation it is order of 1, for pop and multi-pop, all the pop and multi-pop operation combinedly it is order of n. Okay, and then we divide with average to average, we divide by the total number of operations. So we what we get is order of 1. Okay, the same if we want to see with the binary counter. Okay, so let's see it with the binary counter. So let me consider binary uh, some binary counter here. Okay, so maybe this is the value, current value. Now I update it by, okay, same algorithm that you move from the end and you convert the last digit to 1. Okay, so this is how we implement it. I need little more space here, so we can just move it somewhere else. This. Yeah, okay, so 1 0 1 1 0 1 0 1 1. Now this 0 will become 1 and all the ones will be 0. Okay, and 1 0 1 1. We'll see one more, 1 0 1 1 0 1 1 0 0 0 0. Okay, so if you see this binary counter closely, okay, there is one observation to make, that this last digit is changing its value at each step. Okay, so it was 1 here, 1 0 here, then next step it was 1, the next step it was 0, next step it was 1, and so it is changing in all the different say increments. But if I talk about the second value, okay, so it is say 0 0 2 number of times, and then it is changing the value to 1, that is 2 number of times. Okay, similarly if I go for the third value, it is say 4 times 1. Okay, and then it will be 4 times 0. Similarly, the last value, it will be 8 times 1, 8 times 0. Okay, so what we got it from this analysis is that the first digit is changing. So if I have n number of say binary counter increment operation, so the total first digit is changing n number of times. Okay, the second digit, so if I say each changing in one digit is costing you say 1 unit, so n changes will cost you n. The second digit is changing in n by 2 number of cases, that is half the cases, because it is constant for two values, say 1 1, then 0 0, then 1 1. So the change from 1 to 0 and 0 to 1 is happening only half of the number of cases. Okay, so the third digit is staying for 4 number of times. So this will be the structure. Okay, now if I say you are updating it with say some k number of times, or n 2 raised to power n is the maximum number it can form. So if you are updating it 2 raised to power n number of times, okay, what will be the value of this function? So this series is a decreasing GP, and the summation of this, so if I say maybe like n is a constant, the series will be of the form 1 plus 1 by 2 plus 1 by 4 plus, and let me just, and even if it is going up to infinite, the value of this series is 2. Okay, so this will be n into 2. Now this is the complexity of my algorithm with n operations. Now if I want to calculate the average case complexity, I have to divide by the n. So this is the complexity of n operation. Now the average complexity will be equals to n. So I can write like 2 into n instead of n into 2 divided by n, which is coming as 2. So in general, in a binary operation, in a counter, on an average, you are just updating 2 digits. Okay, not more than 2 digits in the binary counter on an average. Okay, so this is what is an output of the aggregate analysis. Now coming to the accounting method and potential method. Okay, so I can go here. So the second one here we are considering is the accounting. This is very interesting method. If I say accounting method is you are in say considering this one example here, this very interesting example, and you all can relate to this example. Okay, so if I say you are working in some say university, you are as a student. Okay, now in that university there is a coffee vending machine where you can go and can drink the coffee. Now the total time consumption is that, so to maintain the hygiene and something, it is advised that if you go in the end when say all the cups are dirty, so we have say some n number of cups there, and the students are going one by one for drinking coffee. So you pick a cup, drink the coffee, keep the cup. Okay, so once you go and all cups are dirty, then you ask the person that please clean the cup, or maybe if it is say the new say idea that where we clean our environment on our own. So suppose you are cleaning all the cups, so there are say n number of cups, say single cup washing of a single cup consumes say order of 1. So the total time consumption will be order of n. And then you will take 1 cup, drink the coffee, will keep that cup. Okay, so the worst case complexity, that so worst case is that when you go at a time when all cups are dirty. Okay, now the best case is that you have a cup available to you, you simply pour the coffee from the machine and then you drink. Now if I say that one operation of say taking the coffee from the vending machine is order of 1, cleaning of a cup is order of 1. So when somebody is getting all all cups dirty, that is the worst case, and he will or she will consume say order of n in that case. So can we use some method to remove that worst case scenario? So we say consider a new strategy now. So instead of say you drink your tea, you wash your cup at the same time. So you pick a cup, you drink the coffee, and then you clean that mug at the same time. Now both the operation will consume order of 1 and order of 1. Okay. So the total complexity, if I say order of 1 means say I say 2 minutes to pour the coffee and 2 minutes for cleaning the cup. So every student will consume 4 minutes, and there is no worst case now because all cups are clean all the time. Okay. So same thing we can do here when we are working on the accounting method. Okay. So let's see. So as we said that we have three set of operation. One is the push operation, another one is a pop operation, another one is a multi-pop operation. Now, as I have already told you that we can remove an element only if it is inserted in the array. You cannot remove an element which is not in the so array here it is we have stack. So unless it is not in the stack, okay. So while inserting the element in the stack, if we consider the cost of removing it, then that would be helpful because then we have no cost while removing the element because the cost has already been taken into account. Okay, so generally we say use a function called C cap, okay, to determine the complexity, okay, amortized complexity of each event. Okay, so for simplicity we can consider some other maybe simple. So I'm considering C prime as the cost, okay, amortized cost of the cups, okay. So of these operations, so the push operation now the cost is so 1 unit in pushing that element, 1 unit cost in popping that element. So I am taking the total cost as, so the total cost now is considered as order of 1 plus order of 1. That is the cost in inserting that element and as the cost of deleting that element. So earlier, if the cost of push operation was say 1, now the push operation will cost again order of 1. Now, if I talk about in a unit, then say if push operation was consuming say 1 unit of time, then now the cost will be, if I don't want to write in the form of order, and I can say if earlier the cost was 1, now an additional 1, the cost is 2. Obviously, it is of order of 1. Okay, so the push operation now will consume or cost 2. Pop operation will now consume cost 0. Multi-pop will now consume cost 0. Okay, so you have a set of push pop multi-pop operation. Now the worst case is that you have all say push operation, then also the average cost will be of order of 1. Okay, now similarly in the same way, if we look at the example of binary counter, okay, so we can if you have seen binary counter correctly, this algorithm, so we are updating all 1 to 0, okay, from the right to left. Once we encounter 0, we are making it 1. So making from 0 to 1 is say set, and making again say 1 to 0 is reset. Okay, so we are accounting the set operation cost to order of 1, and reset operation we consider that cost while setting the counter, okay, setting a digit from 0 to 1. So when we are say changing a unit from 0 to 1, we are at the same time we are accounting for the cost of converting from 0 to 1. Okay, So suppose 1 unit changing from 0 to 1 is costing you 1 unit of time, or maybe 1 rupees. Then say changing 2 digit at a time, so 0 to 1 and 1 to 0 will cost you 2 rupees. Okay, so in each binary counter operation, if you see closely, okay, you are only setting 1 digit from 0 to 1. Okay, so this is the only operation where you set a unit from 0 to 1. Okay, so if we are doing this for only one digit, that means the total cost we are getting is 2 for any binary increment operation. Okay, so each increment operation, the cost C prime will be equals to 2 unit. Okay, and now there will be no cost on resetting the digits, so the total cost can be determined by the same function. Okay, so these are some of the strategies. Now the last method is known as a potential method. This is more mathematical uh, form. So potential. So potential method in a stack. So it is okay. So let me explain this also by one of the example. If you have understood the example, you have understood the method. Okay, so okay, consider a case where say you are traveling for a world tour. Okay, and you have some cost from moving from your home to world tour. So you are moving from say city 1 to city 2 to city 3 to city n, and then you want to come back to your home. Now you don't want to say keep money. You don't know what will be the money at the end when you are done with your trip. So you are on the nth city, so you want to say get that budget with you from the beginning itself. So what you are maintaining is you are maintaining a purse, and you know the cost of say from moving one place to another. The cost is determined by the 100 into the distance in kilometers. So if I say the distance is from city 1 to your city, your hometown, the distance is say 100 kilometers. The cost is determined as a 100 kilometers multiplied by 100 cost. So that is the cost per kilometer you have to spend. Okay, so the cost will be 10,000 rupees to 10,000. Okay, so that would be the cost. Now while saying that you are moving from one city to another city and to maybe different countries, you are maintaining in a wallet the total potential cost, and that potential is equivalent to the distance from your current city to your home into 100. Okay, so that is the cost you are maintaining in your wallet all the time. So once your trip is completed, your global tour is completed, you are on the cn, you will simply open your purse and utilize that cost for moving from that city to your home. Okay, you don't have to worry about the expenditure at that time. The same thing is done in potential method. So worst scenario, the cost for the worst scenario is already accounted at multiple steps in a potential format. Now that potential cost is utilized in the worst case scenario, and you don't have to go for any actual cost or any actual loss. Okay, so let's see this by one example here. Okay, so again if we are moving with the example of stack operation, the potential function is the total number of elements in the stack. Similarly, the in binary counter we can say the potential cost is counted as number of 1 in your counter, okay, at any point of time. So let's see these two examples. What is the total cost coming as of different operation? Okay, this is very interesting. Okay, so as we are seeing here the potential method, and we are defining the potential method, the cost is equivalent to potential cost is equivalent to the cost, the number of elements in the stack. Okay, so at any push operation you are inserting one element in the stack. Okay, so the cost C prime will be equals to the cost of the actual cost, that is C, plus the potential cost. So this I'm representing by function maybe lambda. Okay, so lambda is the potential cost. Now we are maintaining the total cost okay, so the total cost or the amortized cost of a push operation. For any operation, it is determined by the actual cost plus the potential. But say we are calculating it for the push operation. So cost will be equals to the actual cost plus the potential. Now, if I say the actual cost of push operation is 1 unit, okay, and the number of elements in the stack will increase from one to another. Okay, so the potential increment, if I want to say, the potential increment we can define as the potential. Okay, so the current potential that is of the ith step minus the potential of the previous step, that is okay, so this is the potential of the previous step. So this is, say, the cost of maybe what we can say is the ith step is determined by this particular function. Okay, so this is how we are defining the cost. So this is one, and the change in the, if I say the potential, so earlier if there are say k element, now you have inserted one more element, so the change will be of one element, so the cost of push operation will be 2. Okay, so this is the cost of the push operation, that is 2 unit of time. Now the pop operation, if we say, okay, the cost of the pop operation, okay, so that would be, say, again in the same format. So we calculate, so the actual cost is 1 plus you lose a potential of one element. So earlier say there are k elements, now you have say k minus 1 element. Okay, so earlier you had k element, now you have k minus 1 element after say one removal, so the total cost will be 0. Okay, so this is the cost of the pop operation. Now again the cost of the multi-pop operation. Okay, so the cost, so what will be say total number of elements you have removed. Okay, so if you have say removed k number of elements, so if I say the minimum of L comma k as we have defined earlier also, so the cost will be minimum of L comma k. Okay, and you have removed same number of elements from the stack. Okay, so the loss will be also of minimum of L comma k. Those many elements you have removed, so the total cost will be 0. Okay, one last thing is the example of binary counter we can see for the same problem. Okay, so in binary counter we are managing the cost as say number of ones, okay, in the counter at any time. So potential cost is the number of potential is number of 1. Okay, so again utilizing the same equation, okay, let's see the cost of say binary increment. So the cost of binary increment. Okay, so suppose you are say changing ti digits from 0 to 1 and one digit from 0 sorry, ti digit from 1 to 0 and one digit from 0 to 1. Okay, so the cost will be equals to Ti plus 1. Okay, so these are the total number of digits you are changing, then minus the change in the difference on the cost. Okay, so earlier from the beginning, if I say you have reduced ti number of digits. Okay, so you have changed ti number of digits from 1 to 0. Okay, so you have lost ti number of digits. Okay, so ti plus you have now one more digit as 1. Okay, that digit, if I say that one digit you have changed from 0 to 1, so you have one more number of ones. So this is what is written in this function is that change in number of ones from the previous step. So you have reduced ti number of ones because those ones you have converted into 0, and you have one more one because you have converted a 0 into 1. So the total cost will be equals to ti 1 minus ti. Okay, so if I count this, it will be as 0. So total, sorry, it will be 2. Okay, so wait a minute, I have to add this cost. Total cost will be equals to 2. Okay, so the cost of a binary counter is coming as increment is coming as 2 here, which is a constant. So what we have seen in these example, that the worst case complexity of some of the functions were very poor. Say number of here it was say order of k, in stack it was order of n, but the occurrence of those worst case was too low that we could determine the worst case by we could determine the average case complexity by removing the worst case and or by not considering the worst case. This concept is pretty helpful once you see develop some of the algorithms which maybe on worst case is taking more time than the um, on an average case. Okay, and your average case complexity you can determine with by removing the worst case or not considering the worst case. So remember that however the big O is most popular notation, that is the we always want to know what is the worst case scenario. If I run an algorithm or I work on a project, what will be the worst case situation. But if worst case occurrence is too low and we have number of operation, number of say events, we run that algorithm on number of operations, then we don't need to worry about the worst case. We can utilize the amortized analysis and can see the impact of the worst case, and it is not very impactful, then we don't need to worry about the worst case. So this is the essence of the topic. If you have any query, you can write me on my mail ID, which I have not included in my PPT. So this is shakti.sharma1@bennett.edu. Okay, for any clarification, confusion, okay, you can mail me. Okay, good luck guys. Okay.